Recording, Johnny.
Okay, welcome everyone to this session of the seminar on PDEs and applied mathematics that we have been celebrating since 2020. Today we have the honor and pleasure to have with us Professor Fake Ben Belgacem, a full professor at the University of Technology of Compiègne in France. He graduated from the Sciences Faculty of Tunis in Tunisia. Then he obtained his PhD degree in numerical analysis in the University Pierre and Marie Curie, Paris 6, today the Sorbonne University. And after that, he was appointed an associate professor at the University Paul Sabatier in Toulouse and worked there for more than 10 years. Since 2006, he works as a full professor in the University of Technology of Compiègne, and he is also a member of the Laboratoire de Matematica Aplicada de Compiègne. Thank you very much, Fake, for having accepted our invitation to give this talk, and go ahead.
Thank you a lot. I'm trying to, okay.
Yes, we can see.
Okay. This is a joint work with my colleague Faten Jelassi and our two PhD, Aya Bejawi, who is going to defend her thesis by the end of March, and Jun Ma, he is in his second year. And before starting, I would like to thank you for the invitation. And okay. So I'm going to use my mouse to scroll the pages. I'm not familiar with it. Okay, my model here is a diffusing model. It is about the heat conduction in a composite media with a resistance, with a resistant interface. And the result is that is a slowing down of the heat transfer across that interface. And this creates a jump on the temperature field. To be specific here, let me consider the internal domain, which I call the capsule, denoted omega I. It is surrounded by an external subdomain, which I call the matrix, and denoted omega E for external. And both parts of the media does not have the same thermal conductivity, so that the function alpha you see here is a discontinuous function, and the temperature will be a solution to the alpha Laplacian here. So there is no volume source on the PDE, subjected to the Dirichlet boundary condition. So this means that we heat from the external border, and at the interface gamma here we have the so-called Kapitza transmission conditions. The first one is the flux conservation. The flux at the interface from both sides are the same. And each of these fluxes is equal to the conductance beta times the jump of the temperature U. The inverse of this conductance beta is what we call the Kapitza resistance of the interface. It is characterizing the interface, and it may depend on the solution U, on the temperature U, on the trace of the temperature at the interface. For now, to derive formally the variational formulation, I would say that I need to find the solution U that belongs to some space. I will specify it later on. That satisfies the variational equation here for any test function that is subjected to the homogeneous Dirichlet condition on the boundary. And to say some words about the state of the art, where the conductance is constant, there are some works about the theoretical analysis of this variational problem, but also for some finite element methods applied to the discretization of this variational problem. One of these papers had been published in 2015 by our team, but there is other works, different works about this the issues I was talking about. And later on, when the conductance beta depends on the jump of the solution U, and under monotony assumption, which we see here, the Minty-Browder theorem is enabled, and this allows to derive existence and uniqueness of the solution. And this case arises in the biology, and especially in Bordeaux, where I have some colleagues with whom I discussed it, and they work on the electropermeability of the cell membranes. Okay, and here in that case, the solution U is an electrical potential. And the main aim of my talk is to extend those results, that study, to the general case of the conductances. So I assume that the conductance depends freely on the temperature, on both sides temperature, the one coming from the matrix and the one coming from the capsule. And this is the most general case we can consider for this kind of Kapitza conductances. And as we will see later on, this brings tremendous difference in the behavior of the solution U. Here I'm talking about the most commonly used conductances in the cryogeny, essentially, where this conductance is a power of the temperature U from either side, and it is not forbidden to consider both contributions by taking the sum. And these kind of conductance are commonly used in the cryogeny at very low temperatures. Another choice can be found via the Stefan Boltzmann law, and the expression of the conductance is given here, and this kind of conductance is useful for a very high temperature where the interface radiates a fraction of the heat. An emblematic example for the importance of the cryogeny comes from the LHC, the Large Hadron Collider, which is a particle accelerator installed in Geneva. It is a 27-kilometer toroidal tunnel where no less than 9,000 electromagnets are installed. They serve to speed up the particles and to maintain them on their circular orbit. And these electromagnets are more and more performing if they are more and more cold. And a way for cooling them is to use some liquid baths with nitrogen and helium. And at the interface, at the solid-liquid interface between the bath and the magnets, there is the contact resistance, the Kapitza contact resistance everywhere. And this causes a loss of a big fraction of the cryogenic energy. And then we need to understand what happened at those interfaces between the magnets and the liquids. Another example I discovered yesterday from a YouTube video. These are screen capture of that video filmed in a saffron manufacturer where they produce aircraft landing systems, and they use a cryogenic fitting process to join parts that need to be fitted perfectly. And as we see here, we are taking a metal piece from a nitrogen bath, I think. And here also, the Kapitza resistance plays an important role at the interface. Okay, now I come to the mathematical contents of my speech. First, I'm going to bring more accuracy to the variational formulation by setting up the functional framework. Then I will switch to the maximum principle, which will play an important role in the existence result, which is obtained by using the Schauder fixed point theorem. And at the end, I will discuss about the non-uniqueness of solutions on a one-dimensional example. So to start with the functional framework, because of the jump on the temperature, what we need here is to consider broken Sobolev spaces instead of the classical H1 space on the whole domain omega. We are going to consider the functions defined on the that belong to L2 of omega. They are square integrable on the whole domain, but only their restriction to the capsule and to the matrix are in the space H1. Here I'm considering the general case of Sobolev space H sigma with sigma lower than 1, but the case sigma is the case where sigma is equal to 1 is the space on which we are going to work essentially. Okay, so we need here to be aware that our functions belonging to this space are discontinuous functions along the interface. Then we need to consider the subspace of test function. They should satisfy the homogeneous boundary condition on the boundary on the external boundary gamma. And here we have a norm, a semi-norm, which will be well adapted to the study of the variational formulation written earlier. What we can observe here is that this function rho is a weight function. It should be non-negative, and it should not be identically zero. It should belong to the space L alpha, L infinity. It should be bounded, and its integral is positive, is higher than 0. And we can observe that if we are on the whole space V1, this is a semi-norm. Why? Because if f is a constant, that semi-norm is 0. Okay. But if we restrict this semi-norm to the space of test function V0, the constants that the only constant that belong to V0 is the zero constant. Okay, so that the semi-norm will be a norm on V0, and using some compactness argument, we can prove that this semi-norm is equivalent to the full norm of the broken space H1 when we work with the subspace of the test functions. This looks like the Poincaré-Wirtinger inequality when we study the Laplace problem with the Neumann conditions. So now we go back to the variational form, which is now mathematically well defined. We need to find U that belongs to the suburb space, the broken suburb space H1, that satisfies the Dirichlet-Bender condition and is solution to this variational equation for any test function. What is important here to observe is that if we think about the conductances that are obtained as a power of U, so we can replace beta by U to the power Q. And if Q is high, being in the space H1 is not enough to guarantee the well definition of the interface interfacial integral. For example, if we are in the 3 dimensions, that power Q could not exceed 2. And this is a very serious limitation because in cryogeny, the most common exponent is a 3. And then we need to find a solution to overcome this limitation. And that solution is brought by the maximum principle. So if we are able to state a maximum principle on the solution U, if we are able to prove a maximum principle on U, that integral will be well defined, okay? And here, before stepping forth, I need to make some regularity conditions on the conductance beta, which is obtained from B. And I will consider that B is locally Hölderian with an exponent that can be very small. We can even consider only the continuity, but the mathematical work will be more technical. And I need also this mathematical assumption that says that if the conductance is 0, then the temperature at the interface is also equal to 0. So this is a mathematical assumption. In the physical life, this is meaningless because the temperature is never equal to 0 in the real life. Okay? The absolute 0 in the temperature is never reached. Okay, but as we will see, this will be needed to solve some mathematical difficulties. Okay, now for the maximum principle, we need to assume that the Dirichlet-Bender condition is bounded. And if the conductance is not identically 0, U is bounded, and we have this double inequality. So U is lower than the maximum of G, and is higher than the infimum of G. To state this result, we use a very classical approach. We set first M to the supremum of G. Then we consider the function U minus M. And positive part of that function will provide me with a test function. Why? Because v is equal to 0 on the border, on the boundary gamma. Because on that boundary u is equal to g is lower than m, and then this function is 0. So if we plug this function in the variational formulation, we get this equation, and the inner product here will provide me with the square of that test function. And if we look at the integral on the interface gamma, we can plug here m is constant, and the jump of m is 0, so we can plug it here. And if we use the monotony of the positive part function, we will have this inequality. And using these two issues yields that the seminorm of the test function v, which is here, is lower or equal to 0, meaning that it is 0. And then because we are in this space v0, where the semi-norm is a full norm, this yields that the test function is 0, and this says that u is lower or equal to m. So we get this inequality. And to obtain the other one, it is easy to make the necessary adaptation of the approach. The second result, before providing the second result, I'm going to talk about the pathology, the mathematical pathology that arises when the conductance is 0. So if beta is equal to 0 in gamma, if we use the mathematical assumptions, the second mathematical assumption I told it of earlier, okay, so the point here is to try to prove that this operator defined on this closed convex set has a fixed point by using the Schauder theorem. And then we need to check out some properties of this operator T. So it is defined as W is given in that set K. We compute U at the solution of this linear problem. We have W here and not U. And if U or W is a fixed point, we will have a solution to the nonlinear problem. And to show this, we need to prove two results. First, this one, T maps K into itself, and the range of T is a precompact in the subspace V sigma. The first result is obtained through the maximum principle. Okay, so U is equal to T of W, and then U is bounded by M, and it belongs then to the set K. For the second result, for the second part of the first result, we first show that the range of T is bounded in the space V1, okay, and not V sigma. And since sigma is the subspace, the broken subspace V sigma is weaker than V1, then the Sobolev embedding tells us that this is a compact. If it is bounded in V1, it will be compact in V sigma. And to show that it is bounded in the V1, it is easy. We need to follow the classical approach by choosing the right test function. And then through some algebraic manipulation, we can show that this set, the image of the set K by T, is bounded in the Sobolev space H1. Since H1, the broken space V1 is is embedded in V sigma with a compact embedding, then this set will be compact in V sigma. And the second result is to show that T is continuous from K into itself. This is a technical work. It does not require any sophisticated tool. We need to write things and showing that it is Holderian at the end because the conductance is assumed to be Holderian. It is not. It does not raise any particular problem. So that if we look at the epsilon problem, the nonlinear problem with the conductance B epsilon with modified conductance, and we have satisfied all the assumptions required by the Schauder theorem, then the operator T will have a fixed point, and that fixed point will be solution to the nonlinear problem with the conductance. And we have these two important a priori estimates, the maximum principle, and that one was obtained that one was obtained here. Okay. What is important here to notice is that the constant is independent upon it. Because this allows to go to the limit when we try to go back to our conductance beta. Okay, so here the epsilon problem has a solution, and that solution satisfies some nice a priori estimate, and these estimates allow us to go to the limit. And the ultimate theorem says that if the Dirichlet condition is bounded, the nonlinear problem has a solution, and that solution satisfies the maximum principle given here through this double inequality. And the limit uses the convergence results, the weak convergence results in the space, in the broken subleft space H1. Okay, here again, this is a technique that well known in the community of PDE, nonlinear PDE. Okay, so linear problem has at least one solution that belongs to the broken subleft space H1. And now we try to look to discuss how long have I to do you hear me? Yeah, okay. How many minutes left I have?
Maybe 10.
Okay,
No,
that will be
yes.
enough to
Yes, but
discuss, to discuss the non-uniqueness result. So to conduct this discussion, I choose to look at the one-dimensional problem, which is very easy. So the domain will be the segment -1 and +1. The left one is the capsule, and the right one is the matrix. So and the conductivity alpha will be piecewise constant. It is constant equal to lambda in the left part of the domain and equal to mu in the right part of the domain. Here at point z equals 0, we have the interface. And the boundary conditions are fixed to 0 here. The Dirichlet boundary condition is fixed to 0 in -1 and 1 here. So that I can use the adjective cold part for the segment -1, 0, and the hot part is here, okay? So now the problem to solve is this one. Here is the Laplacian equal to 0. The alpha Laplacian is equal to 0, but since alpha is constant, so what we have here is that the second derivative of u is equal to 0 here and there. And this means that u is an affine function here and there, okay? And if we add the boundary conditions, we will have the solution of the former problem. We'll have this expression, okay? And now what we try to do is to use the Picard method to construct the fixed point of the operator T, okay? And that fixed point will be the limit point of the sequence, the Picard sequence, constructed through this recurrence formula. And then this, translating this on the coefficients A and B, allows us to transform the fixed point problem here into another one defined by a numerical function f. So this problem is reduced to that one where an is a sequence of real functions. And if A is computed, we will get B and we will get U then, okay? So now I'm going to consider the first class of conductances. That conductance is governed by the colored part of the domain, the capsule, okay? So it is a power of u at point 0 at the interface, okay? And then the function f is defined here through its algebraic expression, which is a map that starts from R with the domain R and codomain R also. And what we need here is to find the fixed points that obey to the maximum principle. And that maximum principle says that A and B should be in the interval 0 and 1. They should be positive and lower than 1. And the control parameter delta is the ratio of the conductivities, the conductivity in the cold part divided by the conductivity on the hot part, okay? And to study these fixed points, we call for the theory of bifurcation of maps. Okay, and in the case where the power is equal to 1, my function is here, and computing the fixed point is very easy. We can see right away that A equals 0 is a fixed point. So A equals 0 is a fixed point for any value of delta. And we have another one, which is given here. And since this fixed point should be higher than 0, so this is valid only when delta is lower than 1. So for small values of delta, we have two fixed points. And if delta is higher than 1, we have a single fixed point. And for the stability of both of them, we need to compute this derivative. And what we obtain then, here we see the bifurcation diagram. The blue branch represents the fixed point A1, and the red one represents the fixed point 0, A0 equal to 0. And we see that the blue branch is stable until it reaches -1, and starting from that point, it will be negative, and that's why it is removed from the diagram. that fixed point cannot be negative. It should it should satisfy the maximum principle, which tell that fixed point to be higher than 0. And for the fixed point A0, what we see here is that for small delta, it is unstable, and it becomes stable after that. So what we have at last, we have two branches that cross each other. And at that point, there is an exchange of the stability. And this bifurcation point, delta equal 1, is what we call the transcritical bifurcation. For the second example, when the exponent is equal to 2, the function to study, the map to study, is the function f2. We see it here. And we see also here that a equals 0 is still a fixed point. Okay, and it is stable all the time because the derivative of f in that point is equal to 0. And what we see also is that for small delta, there is a critical value of delta. Below that critical value, we have two supplementary fixed points, A1 and A2. A2 is higher than A1. And if we look at the derivative test, the fixed point A1 will be stable because that derivative is higher than 1. And for A2 will be stable because it succeeds the derivative test. So now if we switch to the diagram, the bifurcation diagram, we see here the three branches. The red branch is for the first fixed point A0 equals 0, it is stable. The higher one is for the fixed point A2, it is stable also. And the in-between curve is for the unstable fixed point, okay? So here we have two bifurcation points. This one is what we call the saddle node bifurcation. And this one is the pitchfork bifurcation. And if we continue both branches here, there is no exchange of the stability. So it cannot be a transcritical bifurcation. It is only a pitchfork bifurcation. And because of these 2 points, we can have the hysteresis phenomena because of the abrupt changing of the solution. If we, for instance, we start from the higher branch and we move to the right, and if we reach the tipping point, we will drop abruptly to the lower branch, red branch. And if we go back, if we decrease the value of delta, the system cannot reverse the path. It cannot go back the same path. It will keep moving on the red branch, and when we reach 0, any perturbation to the solution U will be captured by the solution will jump upward and reconnect with the higher branch. So this is the loop of hysteresis. Now, if we look at the other class of conductances, when the hot part of the domain governs the conductance, so that conductance is a power of U E here. And the function J is given by this expression. The control bifurcation parameter is the inverse of the former one. It is equal to mu over lambda, the hottest conductivity on the divided by the coldest one. And if Q is equal to 1, there is nothing special here. The function G has a single fixed point, which is stable. So there is no bifurcation here. And if we switch to the value Q equal to, the expression of G is changed into this one. And if we if we study closely, we made it numerically here. We didn't make computations by hand. And here is that we have also a single fixed point, which is unstable for small values of delta and becomes stable for high values of delta. And so there is a qualitative changing of the solution. And this point is also a bifurcation point. And this kind of bifurcation is a prelude of the flip bifurcation. And to see this, we need to study the composite function G circle G. If we look at if we plot the function G here, and this is the composite function G circle G, we see that this new function has three fixed points. The one which was a fixed point of G, and we have two new fixed points. And if we look at the stability of those
Okay.
fixed points.
Sorry, you have
Yeah.
2 minutes. 2 minutes.
Okay, I'm almost done. Okay. So here we have the diagram of the bifurcation diagram of the composite function. Okay, so we have the same branch here as the one for G, and we see that these two new stable branches of fixed points of the composite function. Okay, and this means that we have a flip bifurcation, which can be compared with the half bifurcation for the continuous dynamical system. So we have a set of 2 points, B prime and B, that are invariant with the function G. So the image of B is equal to B second, and the image of B second is equal to B here. And that set is an attractor. It will capture all the trajectories that we see here. If we start from this point and we compute the Picard's sequence, we see that we are going close to this two fixed point cycle. Okay. Now for the future work, what we need to do is to mainly add the time derivative of the temperature to the equation and consider the transient heat equation and try to carry out the study to find the equilibrium points and to study their stability. So thank you very much. If there is any question.
Yes, thank you, Fake. Thank you for your talk. And we are sorry for all the incidents that we have had today. Yes, we will give the opportunity to the audience if they have any question or comment. Thank you, Charlie. Yes. Does someone have... there is here. Yes. Juan says that the microphone is open for anyone that wants to ask something. Someone wants to ask a question to Faker? If not, I have one question. Maybe it is because I was a bit lost, but these results that you have shown us can be are in high in many dimensions or only one? Because you showed one example of in one dimension, and I started doubting if they could be applied to higher dimensions.
Uh, I guess that the computation, the explicit computations made for the one dimension cannot be realized in higher dimension. Okay, so to illustrate the lack of uniqueness, we need to make some numerical computations in higher dimension. Since the bifurcation is something new to us, we need to learn about the numerical methods used for the to follow the branches of bifurcation. That's what we are doing with our PhD students. We are trying to make some computation in two-dimensional case, and I think the first results confirm the lack of uniqueness. We succeeded in having an example where the diagram with a saddle node and pitchfork bifurcation is also observed in two dimensions. Yeah.
Yes, thank you. I like also the diagrams or the graphic that you showed in order to represent the bifurcations. They were representative, yes. So thank you. Is there any question in the audience? If not, maybe we have had a big delay. We will stop here.
Okay, thank you.
Fine, if,
Thank you again for your invitation.
yes, thank you to you, Faker.
Mm.
And